Welcome back to Learning AI. Today we're going to continue from where we got up to last week, which was using 2D linear regression as a machine learning method, and we're going to implement multilinear regression this time. So that's using multiple input features rather than just one input feature. So just to clarify something, the title that I used for last week, 2D linear regression, isn't as common. You'll probably hear simple linear regression instead. I just use 2D because it makes sense to me that you've got one input feature, one output feature, so it's 2 dimensions. But that's just to clarify that. So let's get into the coding. So for this week, our goal is to implement multilinear regression, and then also to analyze what the effect is of adding more and more input features into our regression model. So let's check that out now. So I've got the full code from last week, and we're actually not going to use much of this. Some of it will look similar eventually, but if you want to start with this code, that's cool, but we're going to actually get rid of just about all of it to there. So all we've kept is just the same libraries we're going to import. We've kept the house data CSV file and how we upload it, and we're also not going to use the columns ID and date because we found that they weren't useful from the last video, and they won't be for this one either. So let's just quickly have a look at our data. So remember, we've got the .head method. Here's our data. Now there are two more columns that we're actually going to exclude for multilinear regression, because remember, for multilinear regression we're not just going to do price against, say, square foot living. We're going to try and predict the price by combining information from all of these variables here, or a good majority of them. Now, there are two columns, two features, which don't have good data in them, and I'll explain why. So the square foot basement and year renovated. Now, the reason why this data is not going to be helpful for us is because when there is no data specified for that type, so for example square foot basement, when there is no basement, a 0 is put in, and then when there is a basement, a value showing how much air in the basement. That's not very clean data for doing regression. It'll make more sense later on in this video and I'll explain it, but we're not going to include those two there. So all we're going to do here is exactly the same here, and we'll add two more to this list here, and that's going to be, we want to remove square foot basement, and we want to remove year renovated. Let's see that now. So we can no longer find those two columns. So those columns, those features have been removed. So we're good to go. So now what we're going to do is we're going to set up our input features. So to start with, we're going to use price as our output feature, right? So price here, and just like last time, it's going to look like this. So set up our features, input and output features. We'll call it Y being the target feature, or the price that we're trying to predict. So that's going to be data frame and price, just like last time. Now for X, which is going to be all the other features, we can do this in a fancy way. What we're going to do is just have everything but the price of the list that of the data frame that we've already got. So if you see what I'm doing here, I'm just going to drop the column price, right, and that'll give us not the price, but everything else, right? So I'll show you the data frame. So if I do x.head, this will show you what I mean. So What I mean is that the price is removed from the data set and we've just got all the input features now. So that's the data set up for us. Now, the next thing that we have to do is implement the multilinear regression model. So I need to do a bit of explaining first before we can get straight into this. So remember last time we had something that looked a little bit like this, y equals mx plus c, or the way we wrote it was actually y equals wx plus b, and it was a little bit confusing. Why do we use w and b rather than m and c? This will make more sense today. So another way of writing it, so here we go, another way is like this: y equals w0 times, put that close, times x0 plus w1 times x1. Now it doesn't look all that similar, does it? But let me explain. So w0 is the same as, that's the same as b. x0 is just going to be 1. It'll always be 1. Now this is sort of, you see where this comes in for, we call it the bias. So it's always 1. Now w1, you probably work this out, in the old equation was just w, and then x1 was x in the old equation. Now, why have I rewritten it like this? Well, you'll see in a minute. The handy thing about writing it like this is you can actually keep growing the equation. So if you've got, that's your bias, and then you've got w1 and x1. If you want to put another feature in, another column, that will be w2, x2. So what that means is that, so x2 will be that, so let's say we had square foot living as x1, and then x2, if we put square foot lot in as well, that would be x2. And w1 would be the coefficient that belongs to this value, or to this this column, sorry, could be any though. And then w2 is the coefficient that belongs to this column. So if we use all our features here, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 features, 16 input features. Our equation we could actually write like this. So x0 plus w1 times x1 plus, I'm not going to write the whole thing out, all the way to w16 times x16. So you're starting to see how we're going to have multi-linear regression here. This is pretty cool. Now, from here, just like in the 2D or the simple linear regression, there's a way of calculating the perfect W value, the perfect weight, such to fit the data as best as possible. And the way we do this is with an equation called the normal equation, which is actually more, it's sort of a, it's an extension or derivation of the covariance over the variance equations that we originally had. So it's still ordinary least squares, but just in multiple dimensions. And there's some fairly nifty linear algebra that goes on, and I won't try and prove it, but if you accept it, again, go to Wikipedia, check it out. It works really well. So what it looks like is this. W equals, and this may not make a lot of sense when you're typing it out, but I'm going to stick a, you can see that diagram right there. Not the diagram, that equation. That sort of shows you what the linear algebra looks like, but it's X transpose dot product by X, and all of that inverse, and then that dot by the X transpose, and then dot by Y. Okay, There's a fair bit going on there. Now, one thing which is interesting, we've got capital X here. That represents a matrix. So things are getting a little more tricky now with multilinear regression because it's not just a vector we're using a matrix. So how does that work? Our matrix is going to look a little bit like this. So if I put so my X, the matrix is going to be a whole list of rows, right? Now, last time it was just a list, it was just a vector, right? X was just a vector of all the square foot living values. This time, we're going to have a matrix because we're going to have more than one column. So we're going to have 2, 3, 4 columns. So each row of the matrix is like each row of data, of input data. So let's say we had square foot living and square foot lot. That means we would have, in our X matrix, we would have X1 being this value here, and then X2 being this value here. And X0 would be 1, remember, because that's the bias. Well, that combines with the bias. So, let's see if I can make a bit more sense of this here. So the first row, so if we use Python indexing, let's say our X matrix is here, and we want to access the 0th row, that will include X0, which is going to be just 1, because that's our bias that we add. X1, X2, and all the way to X16 if we use all the features. So that's what X will look like. When we program it up, it will be a lot more simple, and you'll just go, oh, that's it, that's how it works. So let's see if we can get to that pretty soon. So a few more notes about this. So that this X matrix is going to be 22,000 plus of these vectors, right? As rows, like that. And 22,000 plus, that's how many rows we've got in our data set. So that's X, right? Y is just going to be a vector because it's just going to be one column of prices. Okay, so last thing to mention about this W, this is going to be a vector, and this vector is going to be the same size as one of these rows. And the neat thing about that is that what it's going to look like is this. So W is going to have W0 and then W1 and then W2 all the way up to W16. And that fits our equation up here. So this one equation is going to calculate everything, including the bias value. So last time we had to do a separate calculation, but this time the fancy normal equation actually calculates the bias for us as well. Okay, so let's start programming this. So remember from last time, the terminology, if we want to pull out the proper terminology, this is like our hypothesis, right? Okay, so you know what? Let's just leave that as comments. What we need to do here is, actually I'm just going to copy this in here because so it's nice to see and we can reference it. Okay, what we're going to do is first we're going to add that bias column. So you know how we had, where is it? X0, and X0 is always equal to 1 because it just sort of, it just makes sure that W0 is the bias. If you times anything by 1, it's itself. So it's just making sure that W0 is exactly what it is. So we need to add, before we can plug into this fancy normal equation, we need to add a bias column to our data set. So we're going to have bias here and then a column of 1s. So let's implement this now. So add bias column to X data set, and what I'm going to do is we want it for all columns, so I'm just going to, sorry, not all columns, all rows. So I want to know how many rows we've got. Data frame dot shape. So we've done this before. X dot insert. This is a sort of fancy bit of code. We're going to put bias 1 times rows true. So what this is doing here, this is putting in, this is with the pandas data frame, so it sort of works with that. What we're doing is we're putting in a bias column, and we're going to name it bias, so we're going to come up with a little title here called bias, and we're going to put in that, it's going to be a vector of ones, and we want to make sure that that list of ones, that vector of ones, is the size of how many rows we have in our data set. So that's why I've times it by rows, which is the amount of rows here. So these parameters, you can look them up yourself, but that's just the way it works. So let's just make sure that this works. It's a good practice to do this as you go. So check it out. Bias column, all ones. So we're good to go straight to the normal equation now. Exciting times. Okay. So now we've got that working. I'll just get rid of that table. What we're going to do now is set up our features, input features, and the output feature data for the normal equation to work. So because we're going to do some linear algebra, we need everything to be in numpy arrays. So at the moment we've got it just as values here. So let's convert to numpy arrays. X dot values. Oh, that's actually supposed to be X. Yep. And then we want to do Y, capital Y. I'll just say what we're doing. Okay. So now we've got numpy arrays. We can go straight forward. We can put this into the normal equation. So what I'm going to do first is just sort of break it down a little bit for us. So we're going to work out what the X transpose is. Numpy dot transpose of X. So that just gives us the transpose of X. So we've got that as a variable. It just makes it nice to put it into the big formula for us. So W equals, here we go. This is where the machine learning happens. NumPy.nearAlgebra dot inverse. It's in this linear algebra that we have the inverse function. So we just, or the method. So we need to get that. That's going to take the inverse. So what we've got here is these brackets and a little dash here. We need to put something inside it. We need to put X transpose inside the brackets, and we need to dot multiply that. So funnily enough, call it dot multiply with X. So that's just numpy format there. So dot multiply with X. So we've done this bit here. Time to do this half here. So from there, what we're going to do is dot with X transpose, and then dot with Y, and we're done. So I've run that, it works. Excellent. So that was implementing the normal equation. So pretty cool, and really, like 2 lines of code, you could make a 1 line of code if you wanted to. That's really cool that we can do machine learning with that little amount of code. So let's have a look at what it gave us. So if I print W, we get this here. Now remember what we expected W to be? We expected it to be 17 values representing a bias, and then 16 weights that will be like coefficients inside our hypothesis, inside our prediction equation, to the the different X column values, so the X features. So that's what we've got. We've got 16, 17 values. And the first one is our bias value, and then these are all the weights. Cool, all right. So now let's just calculate the cost. It's good practice, because at the moment we can't just visualize the data in our hyperplane that's been made here, because we can't look into like 16-dimensional space. That's sort of tricky. So let's calculate the cost function just to give us a reference point of how well it actually is working, this prediction function. Remember, in 2D linear regression, we could actually visually see how if the line was way off the data, our cost was really high. And if the line fit it nicely, the cost was lower. So the reason why we use tools like that, like the cost, is when we go into multiple dimensions like this, we can't visualize it anymore. So we need to have some tool that gave us insight into the 2D data that will also carry into multi-dimensional data. So this is why we're using the cost function. So calculate cost function. This is going to be very similar to our previous code for I in range 0, rows 1 for every row. So for every row of data. Now the error is a little bit different this time. We're comparing the same Y value, right? The same actual Y value, the same actual house price. But this time we're going to compare it with, this equation here, right? This is our prediction equation, our hypothesis. We could type this out to the 16, 0 to 16, but that's kind of annoying. We can actually take advantage of the linear algebra dot product to help us out here. So, or sort of dot multiply. So let's do that. X, we want to take the ith row of our X matrix. So that'll be like, I don't know, this row here, but of course it's got the little bias term as well. Got to remember we've got that in there too. And we'll just dot multiply it with W. And that will give us our predicted house price. So we're finding the error between every point and its predicted house price. From there, it's the same as last time. So error sum equals error sum plus error squared. Now you might be thinking, well, it's a bit primitive to use a for loop. Well, it sort of is, but it's easy to explain it. So challenge to you, see if you can do this cost calculation without a for loop and just using linear algebra instead. So anyway, let's keep going with it. Remember our J represents the cost, and the cost is the sort of total average error. So we had that special machine learning function. That's the one there, times by the error sum. And that will give us the cost of the hyperplane. This time we've got a hyperplane because it's not just a line of best fit. Cost of the hyperplane of best fit is, and then we'll put in J there. Cool. So that's our value there. Now, this is actually kind of cool. We can compare this cost to the cost we got from the previous simple linear regression or 2D linear regression video. I've found the values from the last video, and this from using different guesses from ourselves, and then that was using linear regression, the simple linear regression or 2D linear regression. Now if we put in our cost from using all the features, except for a few, remember, let's see if we got an improvement. And we did. So the last one was, it was pretty good. It had a cost of, we had 3 here and the decimal here. This time we got 2. So that's excellent. We've almost halved the cost, which means our hyperplane fits the data better than our line of best fit does. So adding all those extra features helped us out, which is awesome. So that's good. Last thing we're going to do, and this is before we kind of look at using different amounts of features, is we're going to make this applicable. So an actual application where we might use this is, well, let's calculate a house that I don't know the price of if I've got all the other data. So let's just make like a fake house, and we'll put that in. So we'll call it X fake house, right? And before we do that, you know what? I'm just going to show the data ahead. The data head. Oh, it didn't work because it's supposed to be lowercase. Excellent. Okay. Now we need a bias column for our input data, and now we'll put the actual data in. So I've come up. Excellent. That's our fake house data. And let's see what price we get if we put that data in. So first of all, take a guess yourself. I mean, I can't really guess because I already know the answer, but have a think about that. What sort of house, what sort of value do you think it's going to be? So remember this first one, which is sort of similar to this, was about $200,000 and something. So how expensive is it going to be? Well, to work that out, we will predict the price. And to do this, it's actually quite simple. So the machine learning that was done was just to optimize the weights, which was here, optimize W. And W is all we need to actually do our prediction. Because remember, our hypothesis was, which is why our predicted value comes from the hypothesis. Oh, sorry, this one here, predicted value comes from our hypothesis. And the hypothesis is simply the W vector dot multiplied by the X vector. So we've got an X vector, and we just need to dot multiply it with the W vector that we've got, our weights. So super simple. Our price prediction equals the sum of X fake house multiplied by W. So this will do sort of dot multiplication for us. Doesn't need to be in numbing, which is sort of handy. So we go print. Let's see what this gives us. The house price prediction is this many dollars, and we want to do string. Let's round our house price to a nice amount of decimals, just because I don't want to have anything less than 1 cent worth. 2. Okay, so that's just rounding our price prediction into 2 decimal places. Too easy. The house price prediction is $308,000. You know what? That's pretty reasonable. That sounds about right with our data. Let's try manipulating it a little bit. All right, tell you what. Let's make the square foot living area huge. So 650,000. Oh, 6,500. Aha! The house price jumped up heaps. So we've sort of worked that much out. Oh, let's be ridiculous. Let's say you got 10 bedrooms. Oh, you know what? I think our think our house price predictor has a little bit of a fault in it. It's not quite used to having that many bedrooms. So there you go. We found something a little bit wrong with the model. Try one more. What if it was built in 2020? So we're not even there yet. Yeah, that sort of works. So it can look into the future. Anyway, that's kind of cool. Alright, so that's all there is really to multilinear regression. The last thing I'm going to do is just show you the full code. So summary of what we did. We imported the libraries, we processed our data, and that included removing 2 columns specifically, and then we added a bias column to our X data set, ran that through our normal equation, and then calculated the cost function, or calculated the cost with our cost function. That's better. And then we predicted the price for a fake house. So that's what we did today. Now, last thing I'm going to do is we're going to have a bit of fun with this, and we're going to see what actually happens. What actually happens when we start from maybe 3 input features, and then go 4, 5, 6, 7. How does that sort of change our prediction accuracy as we go along? So, well, not accuracy, how does that change the cost as we go along? I've just brought in some code that I've written myself, and again, this will be in the GitHub library, so you can check it out and mess around with this yourself if you want. But it's essentially the same, but I put for loop in here, which goes through the different amounts of input features. So it'll start with like 3 input features, and then go to 4 and 5, or along those lines. So, see what happens. Okay, so the cost, this is what it's doing. It's doing multilinear regression for bedrooms and bathrooms as the input features. So just 2 input features. And then it does it for 3 input features, and then 4 input features, all the way until we get all our input features. And what I'm doing is I'm plotting the cost, which is this value here, every single time the algorithm goes through the normal equation. So with more and more features. And as you can see here, the cost decreases as we get more input features into our data set. So the more input features we put into this, into the normal equation, into the multilinear regression model, the lower the cost. So that's good. Now, last thing, what happens if, remember how we removed these 2 bits of data, which was a square foot basement and year renovated? Wonder what happens when we don't remove those bits of data. Let's put it in. So, looks like it works the same. Whoa, check this out. So, right there and right there are the 2 features we removed, which are now there. Now, if you have a look closely at the cost, so if we've got, where does it appear? Waterfront, square foot above, square foot basement. This one here, so it's introduced here. Let's have a look what happens to the cost. So originally our decimal point was here, and all of a sudden the cost blows up heaps, and then it reduces a bit, and then it blows up again when we add year renovated. And then the other features, you know, as we add more and more, these have less of an impact. And as these are added, we get back down to a reasonable value. But our final value is nowhere near as good as what we had last time. So that's why it's important to make sure you know what data you've got, and know what data is going to actually work for you. So again, without that data, we get much nicer, much lower cost. So that's it for today. Thanks for watching. For next time, we're going to have a look at a better way of analyzing our prediction model, so our multilinear regression. We're going to use machine learning techniques like using training data and test data and other things like that to properly evaluate our model, because we're already in multiple dimensions here, and it's very tricky to visualize if what we've programmed has worked or not. So we need a few tools in our tool belt to be able to make sure that what we program actually works. So join me for the next video. coming up soon.